soon.
Thank you.
Welcome to the webinar session on importance of rheology and particle size characterization organized by Society of Petroleum Engineers, Dibrugarh University Student Chapter. I, Pondicherry, will be the host for the session and keep you posted as we proceed. Grateful on the presence of Dr. Borkha Das Madam, Faculty Advisor, Society of Petroleum Engineers, Dibrugarh University Student Chapter, and other members from Dibrugarh University, participants from Malaysia, USA, etc., and different parts of India. And the chapter is also grateful to Mr. Rajkumar Somendra Singh Sir, Regional Sales Manager, Northeast India, Anton, Parr, India, for supporting us to conduct a webinar. We have two sessions for this webinar. The first session will be based on rheology of petroleum products, and the second session will be based on particle characterization of petroleum products, to be delivered by Dr. Kartik Pondicherry sir and Mr. Sudhanshu Trivedi sir, respectively. Without much delay, I would like to introduce our guest speaker for the first session, Dr. Kartik Pondicherry. Dr. Pondicherry is presently working as the Technical Manager, Rheology in Anton, Parr, India. He did his doctorate in Tribology from University of Leoben, Austria, and his master's in nanotechnology, University of in Germany. He has a vast experience in the field of tribology and rheometry over 8 years. Welcome, sir. You may kindly take over the session and provide us with a distinctive insight on rheology of petroleum products. Over to you, Dr. Kartik Pondicherry, sir.
Kind thanks for the generous introduction. And I would also like to thank Dr. Borkha Das for giving us this opportunity. And today's session is, as you already explained, is going to be in two parts. One would be rheology, and that will be dealt by me. And without going into the details of what Anton Parr is, because like I think most of you already know about that, we would start the session with the agenda. So we go to introduction of rheology, that'll be a bit of basics, and then we go into rheometry, the instrumentation part, and test methodology, followed by some select examples, and then we finally go to asphalt and DMTA. So they are the last two parts of this presentation. And if there are any questions, we could address them at the end of the session. And I was told that after this session, we'll have about a couple of minutes break before the next session begins. So once again, if I forgot to thank the audience, hereby would like to thank the audience as well for joining us for this session. And kind request, please keep your mics muted during the session. And if there are any questions, you can write them in the chat box, or at the end of the session, we can handle them through voice as well. So what exactly is rheology? Rheology is about the deformation and flow behavior of materials. And when you talk about flow, we say water flows. I mean, reverse flow. We say things like oil flows, but you don't say steel flows, because under normal conditions, steel doesn't flow. But imagine you heat steel or iron to 1539 degrees centigrade, and it would start to flow. It melts and starts to flow. So flow is more or less a property of a material, and it's not just about fluids, even other materials flow. And rheometry is where you figure out the flow behavior of materials. So the same logic applies here as well. So when you look at it, you have asphalt or tar or dumber, it's called by different names. So back in 1927, Professor Thomas Purnell from University of Queensland in Brisbane, Australia, he devised this experiment wherein he took these chunks, put them in a nice funnel, and said, give it time and it'll drop. And it did drop. It took about 8.5 years on an average for the things to for a single drop to fall, but it did fall, which only showed that it's a matter of the parameters, you know. So some things could start flowing by effect of temperature. Some things would flow regardless, but you just need to give it time. I mean, simply put, if you're looking at a clock, a seconds needle, you can observe it move, but can you observe the hours needle move? Not really. But if you give it long enough, then you would of course see it move. So this is again the perspective of a window of observation that is very important in order to understand the characteristics of materials. So why rheology? We come across a lot of things in our day-to-day life, like water. I'm not going to talk much about that. But imagine trying to squeeze paste out of your toothpaste tube in the morning. You just can't turn it upside down and then it'll fall. It won't. Gravity is acting, but it still won't fall. You have to apply a minimum amount of force to start squeezing. And then once you put it on your toothbrush and you retract your force, even the paste starts to retract, because there is some elasticity in the flow as well, which makes it retract. So these properties we as consumers might not think much about, but manufacturers do think about it, because if it doesn't behave the way it's behaving, consumers are not going to be happy about it. So that is just a simple example. There are complex examples that we, again, don't concern ourselves with our daily lives, but they are there. Like asphalt, for example, we use it, but we don't think much about its elastic or viscoelastic properties. So that is about rheology, and that is why it is important to understand, not just to make the things better as far as their efficiency is concerned or their longevity is concerned, but also for a feel-good factor. So now we come to the basics of rheology. So when you're looking at this picture, you see that there's something known as a rheology road. And here we talk about both viscous and elastic. So ideally viscous and ideally elastic materials. So if you look at water, it's ideally viscous because it doesn't retain its shape. You pour water in any container, it takes the shape of the container. But imagine taking some nails and putting them in a glass. The nails retain their shape. They're not going to change their shape, or they're not going to take the shape of the glass that you're putting them in, because they are rigid. But they do have certain viscoelastic properties, and you will see what I mean by that in the coming slides. And then there are materials which are in between, like viscoelastic liquids or viscoelastic solids, which have both viscous and solid components. So in order to understand the behavior, one would need to run some measurements. And when you're running a measurement, then you would need a model to describe the whole thing. So in rheology, the basic model that people use is a two-plate model, wherein you have two plates parallelly, and then you have infinite number of parallel laminar flowing layers which do not interact with each other, and those layers form the sample of height h. And then when you apply the force F, this is going to shear the sample, and then you would observe a displacement S. So you know the force, you know the area, you know the displacement, you know the time it took for you to get this displacement, and you know the height. From these limited parameters, what you can get is the shear stress, tau, which is force upon area, the force F upon area, and then you have the shear rate, which is velocity given by displacement over time, and then the height h, which is here. So by simply knowing these variables, you can get the shear stress and the shear rate. And then from these two parameters, what you get is the shear viscosity, which is given as the ratio between shear stress and shear rate. And this was given to us by Sir Isaac Newton back in the 17th century. And this is not rocket science. This is as simple as it can get. If you know the forces and the displacement and the rest of the parameters precisely and accurately, then you can get the viscosity of your material. A few common examples of viscosities. I mean, if you look at water at 20 degrees, it's kind of unity, 1 millipascal second. But if you look at its viscosity at different temperatures from 0 degrees to 100 degrees, then you will see that there is a 6-time drop in the viscosity. Of course, this drop is nothing compared to bitumen or asphalt when you look at it, which goes from 200 Pascal seconds to 1 megapascal second when you go from 80 to 0 degrees. So you are having orders of magnitude difference in the viscosity. That's why I said temperature plays a very important role in the viscosity or the flow behavior of materials. So now comes the role of Anton Parr. So, I mean, as a company, we have been established almost 100 years ago in 1922, but Rheometry has been with us for the past 35 plus years. So what's the basic idea? Again, if you look at the two-plate model, I mentioned that you have the force that you apply, the deflection or the displacement that you observe. It could be the other way around as well. You could apply, or you could set a displacement and then observe the force. The rest, like the area is constant, the height of your sample is constant, and then the time is also measured. So in principle, what you need is the force and the deformation. And if you're able to get these two precisely, the rest of the parameters in the periphery, like the temperature, or you can have the electric or magnetic field, or humidity or pressure, they are in the periphery. Like you are going to observe the influence of these parameters on the rheological behavior. But in principle, what you're looking at is basically the stress and the strain. So your measurements need to be very accurate as far as your stress and strain are concerned. So to do that, you have to also make sure that whatever you're setting or whatever you're measuring is going to the sample here and not to the motor. So what do I mean by that? If you have a ball bearing and you have a shaft rotating in this ball bearing, it has its own internal friction. And this internal friction will interfere or is added to the forces and the strains that are going to be experienced by the samples. And that we want to avoid. And that's the reason we employ something known as an air bearing, wherein your shaft, when it's rotating, is rotating in a nice cushion of air. So it is having a bed of air, which avoids direct contact, or pressurized air, which avoids direct contact with the housing and the shaft, between the housing and the shaft. That means you'll have minimum internal friction when as the shaft rotates. And what do we achieve by this? So a radian is around 57 degrees. And then if you want to think of it, you can think of it as the pi between 12 and 2 of a clock. And then if you're dividing this pi into 500 million pieces, 500 million pieces, you can measure 5 pieces out of the 500 million pieces of this pi. So if you translate that into the Earth's circumference at the equator, you can measure points with a distance of 64 centimeters. That is how accurate you can measure the deflection and set the deflection as well. And as far as the forces are concerned, because as I said, forces and deflections are the heart and soul of measurements here. So if you take a human hair on the finger, extend that arm, then the force that this hair is exerting on your shoulder is what you can measure with the instrument. So that being said, how does a rheometer look like and what are its components? So you have the EC head, EC motor, which is in the head, which applies the normal force as well, measures the normal force as well by moving up and down. And then it also gives a rotational motion and also measures the deflection and also couples the measuring system to the motor so that you can apply the rotational motion. So this is the measuring system. Depending on your sample, you can choose different kinds of measuring systems. And apart from that, you have other accessories or peripheral accessories, which could be temperature devices or magnetic devices or electric devices, which can generate electrical field or humidity. So you have a lot of accessories that go with it in order to, how do you say, to enable us to do measurements which are relevant for the given field. So that being said, what can we do with a rheometer? We have different influencing parameters, as I've already mentioned. You can think about pressure, electric field, humidity, a number of options. And what you can also do is look at microscopy. If you want to look at how your structure of your material is changing by application of shear or application of some other forces, then you can actually do that by just adopting your rheometer with a microscope or even a spectroscope if you want to investigate the behavior or the chemical aspects of your sample. In addition, you can also do dynamic mechanical thermal analysis or tribology, which deals with friction and lubrication, or you can go for powder, wherein you understand the powder behavior. I'm sorry, there's an echo coming. Okay, thank you. And then you can also look at the starch behavior as well. So as I said, you have a choice of geometries, and this is very important for specific products. You will see that with crude oil as well, that viscosity of these materials and the particle size or the kind of particles present in your material are going to determine what kind of a measuring geometry one would use. So here you have concentric cylinders. So the sample would be over here. And then here you have a cone plate system. Of course, this cone angle is exaggerated. Usually you have 0.5, 1, 2, or 3 degrees. And you have a parallel plate system wherein if you cannot have samples in the cone plate system because of the size of the particles, rule of thumb is that the gap has to be at least 10 times the size of the largest particle in your sample. So if that doesn't work out with cone plate system, one could always go to a plate or parallel plate system. In addition, there are relative measuring geometries depending on the sample. Again, if you have slurries and stuff, you can go for some stirrers, or if you have large chunks like in concrete and stuff, you can go for a ball measuring system or also a concrete accessory. So in principle, this is how the accessories would look like. So this is a plate system, plate 25 or plate 50, and this is bob and a cylinder. So this is a concentric cylinder. This part is going to go into this part, and then the gap in between these two, the outer radius and the inner radius, is where your sample is going to sit. There's something known as a tool master, which is attached to the end of the measuring systems. And the reason why I'm saying this is that this chip is going to contain the exact dimensions of the entire sample, the diameter, the length, and the coefficient of thermal expansion, torsional coefficient, and all these things are important because, again, as I said, when you're applying forces and you are measuring forces and deflections accurately, it's also important that tiniest deviations in the geometry, like instead of 25 millimeters, it could be 24.998. Even that third digit after decimal point should not interfere with the calculation of results. So now we come to the test methodology, wherein first we begin with the rotational test and then go for the oscillatory test. So in principle, what you do here is either set the force or the deflection. It might be repetitive that I'm saying this over and over again about force and deflection, but imagine what is rotational speed actually. That means your deflection over time. So 1 RPM is 360 degrees or 2 pi radians, and then rotations per minute would be like 360 degrees per minute or something like that. So you are actually, time is fixed, but you're only changing is the rotation or the deflection. And if you're looking at the torque is force. So force times the radius, of course. So in principle, you are setting the deflection and looking at the force or vice versa. And what do you get out of this? One of the simplest things that you can get out is a viscosity curve, wherein you might see different behaviors. One such behavior could be a shear thinning behavior, which is known as pseudoplastic behavior, such as yogurt or shampoo or face cream, wherein by application of shear or increasing shear, you would be thinning the material. So you're going to make it flow easily by application of shear. And then if you are increasing that, like a starch solution, so when you apply high shear, it's going to stiffen, thicken. That is typical for a starch solution. And for other materials like water or mineral oil, which don't have a structure per se, I mean, they do have a chemical structure, but not a physical, like, polymeric chain or some kind of bonding. There, you don't have any effect of shear rate on the viscosity. So few reasons why you could see shear thinning behavior is, for instance, you can have the particles aligning in the direction of motion, or agglomerates breaking down, or you can have emulsions also deforming in the direction of motion. So principally what they do is they change their shape or their morphology in order to offer the lowest resistance towards motion, ergo offering lower resistance to flow and hence low viscosity. Now we come to oscillatory tests, which are a bit, I wouldn't say complicated, but a bit advanced than simple rotational tests. So here we move from the Newtonian region to Hookean region, wherein Robert Hooke, again in the 17th century, he said that if you look at a spring, the deflection of a spring is directly proportional to the force that's being applied. So the load results in the spring to deflect, and that deflection is directly proportional to the force. And C is the spring constant here. The same can be applied for materials, wherein you get the shear modulus G by dividing the stress over strain, shear stress over shear strain. And of course, this is only valid in the Hookean region. Before I go how to get there, so there is another tiny little detail that I would like to explain, and that is the phase shift angle delta. So imagine a column, a rigid column, and a nice beam suspended to it. You can imagine, a knife that you hold in your hand, and then the blade you're going to bend up and down, and then you will see the deflection. So you're going to apply some force, some stress, and then look at the deflection. And then you bring the force back to zero, and the deflection is also coming back to zero. That means your stress and strain are in perfect sync. And then you could also have another case where you apply a force, you bring back the force to zero, and there's some residual deflection. Of course, this is not like 100% physically apt description what I'm giving here. This is more like a simplified version. But imagine going for a full cycle, and then you will see that there is a lag or a shift in between the input and output waves, and that shift is delta, the phase shift angle delta. For ideally elastic materials, the shift would be zero. For ideally viscous, like water, it would be 90 degrees. And for anything in between elastic and viscous, the delta would lie between 0 and 90 degrees. So why is this important? You saw the same diagram before in a different version, but here you have the stress and the strain and the phase shift angle delta. And the stress amplitude, the strain amplitude, and phase shift angle delta. And from these, what you could get, or what you can get, is the complex modulus G star, which is the ratio between the stress amplitude and the strain amplitude, which could further be distinguished as the sum of G prime and G double prime, wherein G prime is the storage modulus describing the elastic behavior, and G double prime is the loss modulus describing the viscous behavior. And to get that physically, what you could do is simply draw the G star value, the absolute value of G star, and at an angle of delta, and your x-intercept would give you the storage modulus G prime, and the y-intercept would give you the loss modulus G double prime. So if you're thinking about purely elastic material, this would fall to 0, and then your G star would fall on the x-axis, and that would be entirety G prime. The other way around, if you go for a perfectly or ideally viscous material, this would be 90 degrees, and your G prime will be 0, and G double prime will be equal to G star. So this is the simplest way of thinking about the storage and loss modulus. So in oscillatory tests, what one could do is, or one usually does, is an amplitude sweep, wherein you can imagine your finger on your palm and then slowly oscillating it at a very, at a fixed frequency, of course, but tiny amplitudes, like very slow amplitude. Keep increasing the amplitude, and you will see that at some point you will start physically rubbing your finger against your palm. But until that part, what's happening is you only have this elastic movement between your finger and your palm. And that's exactly what you can see here. And this region where you have G prime not getting affected by your strain amplitude is known as the linear viscoelastic range. And here you start to yield, and then once you see that there's a drop, and then the G double prime, which is the loss modulus, is overtaking your G prime, there you have the crossover point, which also indicates the point where your material starts to flow. So up until here, your material is not flowing, but here your material starts to flow. In this particular case, since your G double prime, which is the loss modulus, is already above or greater than G prime, you are in a state of flowing, like you are in a liquid state. So that's exactly what you see here. If you have G prime greater than G double prime, then you have gel-like solid structure. And if you have G double prime greater than G prime, you are in a liquid or a fluid structure. So how does an example look like? Here you have something, again, I don't want to go into details about what sample this is, but suffice to say that it is a thick sample. So if you see here, this squares are the G prime. You see that up until here, they're almost flat. And this is G double prime, which is lower than G prime, which would mean that you are in a gel or solid gel state. There's not much of a difference. That means that it is kind of a weak thing, maybe. So the red dot here indicates the linear viscoelastic range and also the point where your material starts to yield. This is again calculated by the software, and your G prime proposal, LVER proposal, is the value that the software gives you, wherein you can conduct further test, or the amplitude at which you will consider for conducting further tests, be it temperature sweep or amplitude sweep. And the reason for that is that if you're conducting your tests with an amplitude somewhere here, then you're already destroying the structure of your sample. And in order to be able to compare the results, one would run tests where you're not destroying the sample, and this is that region, and this is the point which the software proposes. So a frequency sweep is done usually to understand the time-dependent behavior of your material. So the short-term behavior is given by higher frequencies, and the long-term behavior is given by lower frequencies. And the amplitude is constant here, as you can see, and this amplitude is exactly the one that's being proposed here, or somewhere around here. So it proposes, it's up to you what you would like to consider. You can also do gelation or curing behavior, or test gelation and curing behavior of samples. There you're not changing the temperature, nor the frequency, nor amplitude. You're just looking at it in a window of time. So when you start off, your G double prime, which is the loss modulus, is higher. That means you're in a fluid state. And then you have a crossover at some point of time. And then here you have a stabilization, which means your reaction is complete. You can also look at the influence of temperature. Again, if you have a lotion or a dispersion, which is, or butter, for example, you want to look at freezing temperature of butter, or you want a crystallization temperature of some wax or some other product, even polymers, for example. If you want to look at the behavior of polymers with respect to temperature, you can simply do a temperature sweep. Now we come to practical examples and begin with oils. So funny thing about oils is that most cases they are Newtonian. So in a way, they are not affected by shear rate. And that's exactly what you're even seeing here. So what am I actually presenting? So this oil here is a standard oil. And that you can say it's a SAE certified multigrade oil. And then what you have done here is that you have added different amounts of additives to that. So this is one additive that you added at 2%, and that caused decrease. And then when you added 20% of the same additive, you had a much more significant decrease. And instead of that additive, you added diesel to it, again 20%, you got a much more decrease. So if you're thinking about the properties of the additive, they lie somewhere here. So your additive viscosity is somewhere here. And that by adding 2% is causing such drop, and by 20% such drop. And when you add diesel, it's a completely different story. So the reason why I'm showing this is that oils in principle are shear rate independent. And even if you add some additives to that, you can change the viscosity, but in principle, you're not really changing the shear rate dependence of these oils. But what do they depend on then? Temperature. So you're going from a temperature of 25 degrees to 95 degrees, and you see that your viscosity is dropping to almost half. So if you're looking from here to here, so this is around 30 millipascal seconds, and this is around 110 millipascal seconds. So you can imagine that your oil is dropping significantly with respect to temperature, and the same trend is also observed with the mixtures of this oil with certain additives. And now we come to greases. So here we have, again, I'm sorry if this is all too vague that you have grease 1 and grease 2, because unfortunately we can't label the things according to their shelf name. But suffice to say that these are market products. And this I actually presented at World Tribology Conference in 2017 in Beijing, China. So here you have grease 1 and grease 2. And you see that this is the upward curve, increasing shear rate, and then you'd use the same sample and go back with the shear rate, and then there is a drop in the viscosity, and these are two different temperatures. So regardless of what, grease 1 has the same upward and downward flow, so you're not destroying the structure. But with grease 2, with these flow curves, you see that some irreversible damage has already been done to the sample. So how does that affect the grease? in principle, if you're looking at the data, I said that temperature has a lot of influence, but here you don't see that. So this is 5 degrees, the solid ones, and then the hollow ones are at 35 degrees. So you don't see much of a difference as far as the G prime, G double prime, perhaps a little bit, but not much in G prime. And then the flow point is also not much different between the two temperatures. What is different, however, is that this has a higher G prime, but it also starts to flow at an earlier point. So if you're looking at the absolute values of viscosity, you can say that grease 2 has a higher viscosity than grease 1. But in principle, where do these things matter? So greases are used as lubricants in components which are actually moving against each other. So if you're thinking about tribology, where you have like two components moving against each other and grease is used as a lubricant, this effect of G prime and G double prime and certain other aspects of the grease are having a tremendous impact on the frictional behavior. So this is friction against the sliding speed of your system. So grease 1 has the lowest friction at different temperatures compared to grease 2, wherein almost you see no difference between different temperatures, and at highest temperature you have even a huge spike here, which would indicate that your sample is not is not offering proper lubrication to your system. Now we come to crude oil and the effect of temperature and pressure. So here crude oil has let's say a low viscosity to begin with at room temperature, and at room temperature has high viscosity, and as you increase the temperature, this is at 300 degrees, you have low viscosity. And for this particular test, we use something known as a double gap system, which enables you to have a larger surface area, whereby increasing the torque that's required to am I audible? I'm sorry. Hello.
Yes, sir.
Okay, perfect. I'm sorry that there's a power cut and suddenly my screen stopped. So let me share again.
Okay, sir.
So now you can see the screen again. Great. So yeah, so here you see the effect of temperature. By going from 0 degrees, or sorry, 30 degrees to 300 degrees, you see you have almost a 4 orders of magnitude change in the viscosity of your sample. And if you're looking at the effect of pressure, this is one place where I am not that convinced about the effect of pressure. Of course, in many cases, they use testing of crude oil with under pressure and stuff, under certain conditions, of course. And there you will see that there is a drop. So these ones are under certain pressure, and these ones are at ambient pressure. So there you see a definite change in the viscosity of your samples with respect to pressure. Then we have fracture fluids. I mean, I'm not going to explain what exactly a fracture fluid is because unfortunately I'm not an expert there, but they are used in drilling and stuff and formations and stuff. So here we look at a typical flow curve or viscosity curve. And what you see here is basically that at lower shear rate, so at rest, your viscosity is very high, and when you are going to higher shear rates, then your viscosity. So this one here would be 1,000 times the viscosity of water. And then if you look at the effect of temperature, and you would see the same thing, that you start with 1 Pascal second. So this is like millipascal second. So this would be 1 or 10 Pascal seconds. And by the time you come to 130 degrees, you see that you have a drop of orders of magnitude in the viscosity of your material. And everything signifies that temperature has a very huge effect on the behavior of materials, and pressure does have an effect, but not anywhere close to that of temperature. And here you can see at 90 degrees, the difference between 1 bar and 150 bar. You have a constant, let's put it this way, RPM of close to 43 here, 43 RPM. So you have a constant shear rate, and then you're looking at the viscosity as a function of time under different conditions. So you have 90 degrees at 1 bar, the red, and the drop in the viscosity because of increase in pressure. You can also talk about slurries, for example. So here you see two different slurries, slurry 1 and slurry 2. And the difference between these slurries is that in one slurry, you have alumina powder. And in the other slurry, you have added platelets to this, which would change the morphology of your slurry and also its behavior. The entire, how do you say, like composition is that you added 56% volume into water. So the amplitude sweeps show that there is a difference in the how do you say, G prime values and G double prime values, but not that significant actually. But one thing where you can quantify this is the flow point, wherein you have almost 50 to 60% increase in the flow point. That means in order to make the slurries flow, you would need much higher force or stress in case of slurry 2 as compared to slurry 1. Why is that? It's again, you can imagine that if you have spherical powders, they are a bit easier to make flow, like they offer lesser resistance. But imagine if you have these platelets, like these plates forming around, and then to push them at higher viscosity or higher shear rates, of course, you will have an easier flow because they try to align themselves with the extreme force that you're applying. But just to start making it flow, you would need a much higher stress or much higher force. And if you're looking at the frequency data for the same, you would see that, of course, this has a higher G prime value, but overall they display a plateau, which says that at over longer periods of time, they would show a stable behavior. Now we come to the part where we talk about asphalt. So in case of asphalt, you have different kinds of phenomenon that you could look at. So you can think about the softening behavior, the flash point, and flash point is important because of compaction, mixing, and laying. And then, during those processes, you don't want it to just ignite or combust spontaneously. And then the other properties, like how is it going to behave on the street when you have traffic flowing there or traffic staying there, because flowing traffic is different and staying traffic is different. So you have different other phenomena like rutting behavior, bleeding of the asphalt, or fatigue and cracking. So all these things, I mean, I don't want to comment on the condition of roads because I think every one of us has at some point of time or most points of time experienced bad roads. And those are not just a result of rain or something, but how do you say, the material that's being used. US, they figured this out quite some time ago. Europe figured this time also quite some time ago, and India has now started in 2019. They brought in how do you say? It's a PMB notification. So that's the first revision that they brought in, which specifies exactly the quality of asphalt or bitumen and polymer modified bitumen that needs to be used on the roads, and then we can ensure that the roads are proper. Of course, there are other parts as well, like you need proper concrete and you need proper mastics and stuff. But in principle, if the characteristics of asphalts are as specified and as per standards, then one could expect proper roads. So there are different methods. This is again an American method, which is like Highways and Transport Organization, American Association for. And then here you have this you have already seen, same thing, G star, stress amplitude, strain amplitude. And here you have the original binder, which means original asphalt. And then you have rolling thin film oven residue, and then pressure aged vessel residue. So different kinds of aging processes. So for each of them, the input strain. So this is the strain. So sorry, this is the strain that would be different. So here you're going to apply the strain and then look at the stress, corresponding stress. So you have the frequency constant, and then you have all the sample size, which is already defined. And the result criteria, again, depends on what kind of sample you're testing. I mean, this is just to give you some idea that there are norms which specify how the asphalt is supposed to be. And this is basically for original binder. And oops. So here, if you're imagining a sample has been tested and at different temperatures, because you're talking about temperature dependence as well. There are videos on YouTube or some other video channel, how do you say, network, wherein you see people trying to walk on a very hot summer day in the North Indian cities, and their shoes or chappals are actually getting stuck on the asphalt. I mean, I experienced that myself as well. So here in Hyderabad, that means when the temperature is increasing, the how should I put it? The asphalt gets so viscous that it gets soft, and that softness is actually causing our feet to dig deep into. I mean, if we with our weight can dig deep, imagine what will happen with larger vehicles. But anyways, so if you're thinking about grading of asphalt, you have jumps of 6 degrees centigrade starting from 64, 70, 76, and 82. So if the G star over sine delta is greater than 2.2 kilopascals, then your sample has passed. So this sample passed for 76 degrees centigrade, but not for 82 degrees centigrade. And then important point here is that those things are for actual asphalt original binders, or even the aged binders, but doesn't matter. I mean, I don't say they're one and the same, but they haven't been modified per se with any polymer addition. So what happens is that nowadays polymer is being added, and those kind of tests are not going to give you much of an information about the effect of polymers on either the fatigue behavior or the rutting behavior. So for example, here if you see, this is a flat, how do you say, bar, and you can see that the air is, light is passing through, which means that there is a gap, and that's actually called rutting. And here in this particular case, it's 15 millimeters. And this needs to be avoided. Multiple reasons. First thing is that rutting is not good for vehicle, for navigation. And the other thing is that if you have rutting, then water can come and stay there, and that would cause aquaplaning. So a number of things that can happen. So in order to understand those behaviors, what one could do is do a creep recovery test. And there, what you are actually doing is putting the sample through some rigorous creep cycles, and then see how they recover, how they respond. So if this is the network that was originally there, and here by doing this, you're actually breaking the network and seeing the limit to which this sample can go. And the final part, excuse me, would be about dynamic mechanical thermal analysis, also known as DMA or DMTA. So what is the difference here? Earlier, we saw the exact same slide, but we were talking about the shear modulus. Here, we just go a little sideways and talk about the elastic modulus. So this is E star, and then this is E prime, E double prime, and every G is replaced by E, but at the end, the theory remains the same. You have an input signal, you have an output signal, and then you have the phase shift angle delta. So in order to do this even more efficiently, what we offer is something known as a twin drive or multi-drive instrument. So with a single drive, what one could do is torsional measurements or shear measurements or tension measurements, wherein you have a strip, you will see this later, and you are going to expand it, and you can have a bar or cylinder here, and then here you can have simply between two plates. But by adding an additional linear drive, one could change this into a full-fledged dynamic mechanical analysis tool and do 3-point bending, dual cantilever or single cantilever bending, or you can do tension and compression as well, but within a certain limit. So why is this important? Because if you're measuring polymers, I mean, polymers like are like being used indiscriminately everywhere in our daily lives. So in order to understand their behavior, if you want to analyze or characterize them, you have to again think about their other properties. Like, not all polymers can be tested in the same way. For instance, if you have a foam or a reinforced polymer, the stiffness is like orders of magnitude apart, and then you can't use the same kind of tool or the same kind of setup in order to investigate them. So depending on the stiffness, you choose an appropriate test strategy. For example, if you have torsion and extension, you could use SRF fixture, or here, if you have a polyethylene film and then you want to look at its extensional properties or even fibers, you could do that as well. So you have options. I'm going to skip this. And these are the 3-point bending measurements or the cantilever systems. So it's better if we actually have a direct look at it in. So here you see this is, you can call it a sellotape, for example, that you are looking at the extensional behavior of your sellotape, and that is being tested here. Or if you want to look at the tear properties of this carbon film, you could do that as well. And then this is compression. I think this is called an OSHI. So these videos actually provided to me by a colleague of mine, Ashish Kumar from Anton Parr in Australia. And yeah. So in DMT, we could do a lot of measurements. And if you just look at it, you will see that these measurements look exactly similar to the other measurements that we talked about. Amplitude sweep, temperature ramp, frequency ramp, humidity, of course, is something different, and time sweep. So at the end, it's the same thing you're doing. All you're changing is you're going from shear to elongation or extension. In addition to those, you could also do creep recovery tests. So you're going to suddenly apply some stress, some strain, some strain, and then you're going to leave it at that point and then see how it recovers back and how long it takes to recover back. And you can do stress relaxation, and you can also do some tensile tests, of course, again, within a certain limit, and thermomechanical analysis. So in thermomechanical analysis, what I'm saying is that if you're elongating a polymer, let's put it this way, and then you're looking at its elongation with respect to temperature. So the rate of elongation is different when it's in its glassy state or when it's in its non-glassy state. So from that, you can actually figure out the first thing, like the thermal expansion coefficient, and the second one is the glass transition temperature as well. But primarily, you would look at the thermal expansion coefficient, and glass transition, you can do it in other multiple ways as well. So how do you do the glass transition? So you can look at the peak. I mean, you will see this. There are multiple ways, and this is another reason why when somebody is doing glass transition or talking about glass transition, it's important to mention which of the criteria was actually used to measure glass transition temperature or calculate glass transition temperature. So here you have G prime or E prime, sorry. This is the E prime, the red curve. And then this one here would be the E double prime. And then here you have the tan delta, which is the damping factor, and delta is a phase shift angle. And this is with respect to temperature. So one way of determining the glass transition temperature is looking at the tan delta, maximum of tan delta. The other way would be to look at the maximum of E double prime, that is the loss modulus. Another way is to look at the inflection point. So here you draw the tangents and you see at what point you have inflection, and that would be considered as glass transition temperature. I mean, each of them have their own advantages and effects, but again, it is important whenever you're doing this to mention what method was used to calculate the glass transition temperature. Examples. I mean, if you have some sulfur added to your polymer, what happens? So here you're actually seeing that with the increase in addition of sulfur, so from 1, 2, 3, and 4, I don't know exactly what percentage was used, you're actually moving the glass transition temperature to a lower point. If you take this as a criteria or this as a criteria, you see that the trend is the same, but what would be different is the absolute value of glass transition would change depending on what method you have used to calculate glass transition temperature. And you could also look at the compatibility of polymer blends. So if you are just taking two different polymers and then blending them together, are you going to get like 100% compatibility between them? Are they going to mix with each other properly? So in this particular case, you have two different polymers. And you see that here you have two individual peaks of E double prime. That means those individual peaks are indicating that you have two glass transition temperatures for two different components. Had there been 100% compatible, this wouldn't have been the case. So here you see that peak or PET or peak with so you have peak, that's the solid line, and then this PEI, and then this is peak with 60% PEI, and then each of them has their own single peaks, which makes it a compatible blend. But if you have an incompatible blend like peak and PES, then you have a double, how do you say, peak, which indicates that these blends are not compatible with each other. So again, this is just one single example, but you have other numerous examples where DMA can be useful. So, and if interested, Parr can also offer at some of time a dedicated session, because that will go for 1 hour, 1.5 hours just for DMTA, when you will go deeper into not just the theory, but also the practical applications of DMTA. So with that being said, I would like to thank you all for joining this seminar. And if you have any questions, I would be more than glad to answer. So thanks to the organizers for this. And yeah, thanks for your audience as well.
Thank you, Dr.
Hello.
Kartik Pondicherry, sir, for your wonderful presentation.
Thank you.
We would like to request, yes, sir. We would like to request all the participants to drop their queries in the chat box itself.
Sir.
Yes, sir. Yes, Sudhanshu.
Yeah, very good afternoon, sir.
Yes,
Uh,
good afternoon. So,
so
we're
can I?
starting the session by 5 p.m.
Oh, fine, absolutely fine. Sir.
Thank you, sir.
So, good afternoon. Myself, Sudhanshu. I'm the technical manager for Particle Characterization Group, and today I'm just taking a small review regarding what is particle size and how systems look like, how it works, what is the terminology. And then afterwards, I would take a few examples of the petroleum industry, where it is used and for what application it is used.
Sir,
So I'm just
sir, your
taking,
voice is not clear.
are you able to
There
hear
is,
it now?
Yes, sir.
okay, sir, okay.
Okay. So I'm just starting, there are a lot of particle characterization methods available in the market from 1700 to date. And if we see, these are the different techniques for getting the particle size analysis. Starting from sieving, sedimentation, image analysis, SAX, and SEC, laser diffraction is one of them, dynamic light scattering. So all these techniques are basically used for measuring the particle size, but it doesn't matter in the same way as one system measures. Particle size always measured by different properties, using different properties of a particle. It is not measured directly. It is measured by measuring one property of a particle, and then they convert the information into the size. So it's basically, I would say, all these methods are indirective methods, not a direct method for particle characterization. But these techniques can be selected on the basis of your usage. Suppose your application area is surface of the particle, then definitely you need to go for the image analysis kind of systems. If your application is volume based, definitely then you have to go for laser diffraction kind of principles. So different properties of your application will let you know the different instrument, but all these instruments are available for measuring the particle size. If I go a little bit more, then I can say this is a particle size with respect to the range. Like from 0.1 nanometer, you can go up to 10 mm, and you can select any kind of instruments which is mentioned here. So every instrument has its limitations with respect to the size and technology, but laser diffraction is one which has a broad range from 10 nanometer to say it can go up to for the analysis of the particle. So this is the reason why laser diffraction is more famous for particle size analysis than any other methods. Now I'm coming to particle size analysis. When we say particle size analysis, first thing comes into our mind, what is particle? Particle is any condensed phase tri-dimensional discontinuity in a dispersed system. If I say this, means any small matter, either it is solid or liquid, any shape, any material, or any dispersion or emulsion, it is said to be a particle. Now, measuring particle size or how it is measured. All particles will induce light, and the technique which we are talking about, laser diffraction or dynamic light scattering, they are light scattering based on light scattering principles, and it's based on intensity experiments. So these systems are based on intensity experiments. There you will get the particle size. Now, why we are measuring particle size is another big question. How does it matters? What it affects actually the production process, and it also influences the final properties of the product. Means you are actually, by controlling the size of your materials, you are actually making money. You are saving a lot of money or making a lot of money. If I say final properties, the question arises, which kind of final properties? I will say it could be reactivity, It could be a dissolution rates, for example, catalyst in your cases, tablets, stability of suspensions, that is sedimentation or creaming, that is again your area, efficiency of delivery, that is errors, texture and feel, that is for food industry, appearance like coating and inks, viscosity, that is slurry. You can use particle size as well as rheometer for viscosity. Then packing density and porosity, for example, in ceramic. So these kind of final properties is controlled by controlling the size of the particles, and actually you can develop a good quality product, or you can improve the quality whatever you are looking in your product. So controlling of particle size is very big deal, and it's influence a lot with respect to your particle size of your final product. So how do we analyze? As I told you that laser diffraction is an indirect method. Not only laser diffraction, many methods are indirect methods. So what we do, we are measuring optical property and assuming its sizes. Error may be a problem in this case. Hello, yes. So actually, yeah, hello. Uh, I'm continuing again. So since this is volume-based application, so it's considered that all the particles are in sphere, and the shape plays a major role because real particles are not sphere. So more your particles are away from sphericity, more problem will come in reporting the result. But since if you have a volume application, then it's better to have a laser detection, since it is high reproducible and it's a perfect quality control tool. Now, there are two kinds of systems available in the for particle characterization. One is dynamic light scattering base, another is laser diffraction. Dynamic light scattering base comes from the range of 0.3 nanometer to 10 micron, and laser diffractions comes in the range of 40 nanometer to 2.5 mm. There is a slight overlapping range between these two systems. Both measures the particle size, but DLS is uh, purely dedicated to the nanoparticles, and laser diffraction has a range from nanoparticles to upper 2 mm range. So these are the systems, how they look like. So when we say laser diffraction is basically from nanoparticles to coarser particles. And there's another system which dynamic light scattering system, which is light laser, that is from the purely for nano range. And you can do zeta potential and stability test of your samples in this system. And both systems goes to petroleum industry. The major system is particle size analyzer, which is used for catalyst, oil in emulsion, emulsion in oil, and for these kind of products, they are using particle size analyzers. So I will take you a little bit about the particle size analyzers now. Particle size analyzers basically come from the range of 40 nanometer to 2.5 mm. And you can do two kind of analysis, that is dry analysis as well as liquid analysis. Dry and liquid analysis may be liquid emulsions or solid in liquid emulsions, and dry analysis is something called solid in air dispersions. So basically, if you want to measure the dry sample as dry, then you can choose the dry option. And if you have any other samples, you can disperse them in a liquid medium, and then you can analyze the sample. So particle size systems basically come in two formats, dry and liquid. Now, I will give you a little history about the product that we are promoting, particle size analyzer. Earlier, actually, this particle size analyzer was world's first particle size analyzers that was developed by a company called Silas. This Silas, this is the first particle size analyzer that you are looking at. It is developed in 1967. It's the first particle size analyzer of the world. And then this company is basically making the optics for the military operations. This systems is very robust, compact, and now we have purchased this our corporate office in Austria. So we have purchased this system now, and we are promoting from last 1 year in India, and we have sold many. So actually, it is a very standardized and local, high level of expertise, fast and efficient, and we have developed a new software called Calliope to operate this instrument, which is a single page software, no pop-up. So now I'm coming to the principle, how it works. Laser diffraction is a very simple first law of physics that we say when you pass the light from any sample. So bigger particles scatter light at a narrow angles, and a small particles scatter light at wider angles. So laser diffraction systems consist of nothing but the laser at one side, and then we pass the sample in front of the laser, and we try to collect the diffracted light at various angles. This is a very simple principle of how laser diffraction system works. So as I told you, angle depends on particle size, that bigger particles will scatter light at narrow angles and small particles will scatter light at wider angles. So you will, once you put the laser on, this kind of ring shape structures will fall on the detector. So by the angle, we can really consider what is the size of the particle. This is how it is correlated. And then there are two optical models where basically we take the value intensity, how much intensity is falling on the detector, and what angle, means I and theta is taken into consideration from this experiment. And then we put in a appropriate optical model, and then we calculate by using Maxwell equation the entire distribution of the particles. So you can see that we have measured the different diffracted intensity, and we sum it, and we plot a correlogram, and that correlogram is again represented as a distribution graph. This is how the result obtained by this particular system. As I told you, there are two optical theories. So there are two theories, one by Fraunhofer, second is my theory. Fraunhofer is the first one who introduced this theory for the calculation of particle size distribution, and he considered that all particles are opaque. This is the theory that Fraunhofer gives, that the particles are opaque and you get only the diffraction from these particles, and or particles are larger than 50 microns. This is what he considered, and me said, no, it is not possible. Particle might be having some scattering, absorption, diffraction, everything which should be there. So he put a advanced theory, which is called my theory, now which is available for nanoparticles also. So now, if you don't know anything about your particles diffraction behavior, so people used to select Fraunhofer, and if you know the particle scattering behavior, then people used to select me theory. So both the theories are available in the systems in any particle size analyzer. So these are the two optical theories which are available. So one says particles are opaque, and one says no, it is not like that. So if you, I take you in the real thing, yeah, this is the real thing. If your particle is transparent, there is no absorption at all, then refractive index is considered, absorption is considered between 0.01 to 0.03. And if your sample is having absorbing behavior, so having all optical behaviors, then absorption is considered to be greater than 0.1. And if your particle is opaque, so there is no absorbance required for this. So these are the optical properties that you take into consideration when you are samples. So there is a transparent like glass emulsions or glass beads or emulsions, then absorbance should be between 0.01 to 0.03. And if you have optical behaviors in your materials like metal oxides or small particles, then your absorbance should be 0.01. And if you have a bigger particles like coal and all that, then you need not to take any absorbance into the consideration. So these two theories, transparent and absorbing, is introduced by me, and Ronopro introduced the opaque theory. There are two different theories that are used for analysis of the particle size systems. Now I will show you a little bit of the particle size analysis. So basically, we have configurations with respect to the applications. So we have one laser system, two laser system, and three laser system. This indicates one laser system, two laser system, three laser system. Again, we have a configuration called liquid and dry, and liquid and dry both. So we have various models. We have at least 9 models with respect to the applications. If you required a higher range with liquid and dry both, then we will offer you 1190, something like that, different configurations. You can see here the top black color is the liquid dispersion, and here this glass covered is a dry dispersion unit. This is how it looks like. Now I'm telling you the configuration. Basically, the laser, any laser diffraction, this is the basic laser diffraction system diagram. You have a diode laser at one side, then you have some lens arrangement. After that, you pass the samples, and on the you have some detector arrangement to capture the intensities. What happens when you shine the laser and sample is passed in between, then there is a scattering or diffraction, whatever you are getting in the back, that is covered by additional detectors, means I, intensity falling on detector, and the angle by which they are going. So I and theta is captured, and as I told you, either you choose Fraunhofer model or me model. Those values are put it by using these optical models, and then Maxwell equation is used to calculate the entire distribution. So if you see 990, it ranges from 200 nanometer to 500 micron. This is a single laser system. If I add one more laser to it, then this range extended to lower range, like 40 nanometer. From 200 nanometer, it goes down to 40 nanometer, and range become 40 nanometer 500. And if I
Hello.
increase one more, yeah, hello,
Sir.
yeah,
Hello.
yes, tell me.
Sir, I have a question, sir. Sir, how can we test size?
Sorry to interrupt you, sir. So the questions will be addressed at the end of the session. You can drop
Okay,
down
sir.
in the
Sorry.
chat box.
Okay.
Sudhanshu, sir,
So
you may
if
continue.
yeah, okay. So if I give one more detector, and then my range becomes to 2.5 mm. So this is how single laser, dual laser, and third laser systems come. So depending on your size requirement, you can select the proper instrument and the proper lasers for. So you see, I have compiled them. So we have 3 models where we can go from 200 nanometer to 500 microns. Then we can go from down 40 nanometers to 500, and the highest version we can go 40 nanometer to 2500 microns. So 25 micron actually is a very big particle. You can say 2.5 mm, which is visible by naked eyes. So there is no use of having such high instruments for the analysis of such big micron particles. Basically, these systems are designed for particles below 1000 microns. If I'm coming now coming to application, I have not given a very big presentation. It's a small compact presentation, and try to put it short and clear. So when I say application, you name the application, particle size is required, like building materials. Building materials, I say cement is the biggest application. The early strength of cement is controlled by controlling the particle size. Suppose we have a cement of a bigger particles, then the chance of having the crack or is, the settling time will be more than 1 month, something like that. If you have a complete blend of 10% finers, 10% of coarser particles, and rest particles in between, then it is called a good strength and early strength, high strength cement, which has early settling time. So the particle size controlling of the cement industry will give you a different grade of cements by controlling the particle size. Similarly, we have applications in chemicals and petrochemicals, food, drinks, and pharmaceuticals. If I take the example of the chemical, then chemicals are basically like titanium dioxide. Titanium dioxide, when it is a coarser particle, it comes look like yellowish in color. When you keep on grinding the titanium dioxide to the nano levels, then it becomes a whitish, highly bright whitish. And this titanium dioxide is used for coating on bunkers, military bunkers, so that nobody can see them. Because when this titanium dioxide become nano, then it become a total light reflector. Again, one more example, you have heard about the paints, talking about light reflector. So there is nothing, there is again, they are mixing titanium dioxide in the paints, and that titanium dioxide range is again in nano. So it reflects the light. That's why they are promoting it as a paint with a reflection. If petrochemical, I will take a little bit elaborately because this is your application area. Food and drinks, I can give you example of chocolate. In chocolate, you see the mouth feel or texture of the chocolate comes by controlling the particle size. If you are having a particle, very small particle or very fine particles, then when you eat the chocolate, it will stick to your tongue. You will not feel good. So you will not take that chocolate again. But if you have a chocolate with a little more bigger particles, then it will dissolve slowly and you will feel the taste of the chocolate. So this is how chocolate industries use the particle size analyzer to control the particles of chocolate to get you a proper texture and mouth feeling. In pharmaceuticals, I will take an example of tablets, like you must have heard about the fast relieving drug and slow relieving drug. Fast relieving drug is nothing, but it is grinded more. When it is grinded more, it is in nano. And when it becomes in nano, when you take tablet, it easily or fastly dissolve with your lungs and it give you a fast relief. That is called fast relief drugs. And if you have a particle bigger and you are taking that bigger particle tablet, then it dissolves slowly. So you will get a relief slow. So these are called slow relieving drugs. So this is the examples of each category. Now I am talking about the petroleum applications. Actually, there are many applications in petroleum for particle size analyzers. You have the requirement of particle size analyzers as well as the laser diffraction based particle size analyzers. If I talk about the petroleum industry, so range of applications come from exploration, completion, processing, and refining. In all three stages, you require the particle size analyzers. When you are exploring or drilling front or proppants, then also you require particle size analyzers. Oil in water emulsion or solid particles processing, then again you require particle size analyzer. And for the catalyst, definitely you require a particle size analyzer. So the technique used for all these process is laser diffraction, dynamic image analysis, acoustic spectroscopy, and surface area analysis. So basically, all these techniques are used in the entire process of petroleum. So I will take one by one. If I say when you are exploring the fluids, so there are three types of fluids basically: water-based mud, which you called WBM, and then is must and synthetic base flood. So basically, WBM, OBM, and SBM are the three kind of fluids that you basically uh, explore. And WBM is basically water, then clay, and other chemicals. And most common is bentonite. Other chemicals for viscosity control like shale stability, enhanced drilling rate, cooling, etc. is done in this process. In oil-based must, basically base fluid is a petroleum product such as diesel fuel. And if I say synthetic base fluid, basically is a synthetic oil, nothing else. What particle size do in this drilling fluids? Basically, standards methods are used. Old methods like sieve and sedigraphs or sedimentation is basically used for this drilling fluids. So to always report the residual that it should be greater than 75 microns or should be less than 6 micron. And laser diffraction basically report this positive distribution information by using D10, D50, D90. When I say D10, D50, D90, it means D10 is 10% particles below this size, D50 means 50% of the particles below this size, and D90 means 50% of the particle below this size. And this technique is very quicker and reproducible. So basically, their sieve and sedimentation is the technique, and now it is replaced by laser diffraction principle. If you see the drawback of sieves, sieves basically measure the second largest dimension of any particle. It doesn't because when you suppose you take a pen and you put it through one hole, 2 micron hole, and keep on flushing that pen with water. The time will come when it will pass through that 2 centimeter hole, because it becomes stand, tilt, and it will go between. But it is not the correct interpretation because pen size is not 2 centimeter. So this is the drawback. You can only measure the second largest dimension with sieve, and nanoparticles cannot be resolved with this technique. That is again the drawback. When you are saying 6 micron below residual, so residual 6 micron below is actual or not? That is a question, because below 10 micron or 5 microns, sieve is not a good analysis tool. Similarly, sedimentation technique is now also very old. Sedimentation technique take lot of time. It's a time consumable technique. Bigger particles settle down. Basically, sedimentation, what happens when you put the samples and it starts settling down. So you take the timing of sedimentation, by how much time it is settled. So in that case also, there must be some planetary samples which will not go directly. They will float within the oil, and then they will keep on floating and they will settle down. So they will not settle down straight. They will settle down randomly. So these are the disadvantages. That's why now people are using laser diffraction. And for example, I have given one example here that for barite, we use a refractive index of 1.64, and absorbance we have taken 0.1, and sample is prepared in 1.33, that is water refractive index. We have added 1 dispersant sodium pyrophosphate, and then we paste the right water with dispersant, add to the system, and we have given ultrasonication for 60 seconds, and we measured it, and we got the answer what we desired in the form of D10, D50, D90. So this is one application of drilling fruits that can be done by using particle size analysis. Then in production, there is a flood separation. Separation means you want to separate all phases. You need to measure the phase separation. You improve by adding surfactants. Need to measure ppm oil in water. Like I told you, water in oil, oil in water. These are the two applications majorly used for the flood separation. So required to measure if pumping water into ocean, offshore rings, or oil is valuable, separate as much as possible. So possible to differentiate oil droplets from particles. So this is what major applications in flood separation. And not only the separation, but also the stability is one where you will use nanoparticle size analyzer or DLS technique, because in DLS technique you can measure the stability, and that stability again, you want to promote the phase separation, you want to recover oil, discharge water, and may want to add water to oil to reduce viscosity and easier to transport. So these are the applications which are answered by using laser particle size and nanoparticle size, both in case of production. So this is one more major applications that we have in your application area. And there is one more study which is called emulsion study. Emulsion study you want to do without dilation, or you want to predict the dispersion stability. That is called zeta potential. And zeta potential is measured by using DLS technique or DLS system. That is again a nanoparticle size analyzer. One major more last applications is the laboratory that refining the catalyst. You refine the catalyst by using the size, shape, and specific surface area to ensure the catalyst performance, and this is done by using the particle size analyzer. So I know IOCL is using for all these applications. In for grease also they are using particle size analyzers. They are using this phase separation. For phase separation, they are using particle size analyzer. And for catalyst, they are using from long back, from more than 18 years, they are using this particle size analyzer for controlling the catalyst. This is all from my side. The summary is that we can do drilling fluid, propants, oil, water, solid separations, and catalyst. This is what we can do by using the particle size analyzers. And this is our software that we use, which I told you. So thanks from my side. This is all from my side. Now we can have questions and sessions or whatever you say, sir.
Thank you, Mr. Trivedi, sir, who is presently working as the Technical Manager, Particle Characterization in Anton, Parr, India. Here to fill the feedback form which has been shared in the chat box. The recording of the session will be also available in the YouTube channel of SPE Dibrugarh University chapter. Now, at this point of time, is there any query based on a presentation? You may kindly drop the queries in the chat box, and the concerned speaker will address the queries. There is a query.
Zeta potential cell. How do you define zeta potential? Zeta potential is nothing but the measurement of the stability of your suspension or emulsion. How stable your suspension or emulsion. In easy word, if I say every product has an expiry date mentioned on their product, like drugs have expiry date, or simple you can say medical drugs. कोई भी syrup है उसका एक expiry date होता है. It has an expiry date. That expiry date is nothing but is a measurement कि your emulsion will not remain stable, or this formula will vanish after this date. So zeta potential is nothing but the measurement of the stability of your suspension or emulsion.
Thank you, sir. I've addressed the query. Is there any other query based on importance of rheology and particle size characterization for petroleum?
Hello.
Yes.
Yes, sir.
Hello, sir. This is Shivakumar.
Yeah, sure. Please tell me.
Hello. Sir, am I audible?
Yeah, sure. Yeah, you're audible. Please tell me.
Sir, how can we test the shape of nanoparticle?
Shape of nanoparticle can be done by using another system, which is called shape analyzer. That is a
Okay.
dedicated system for that is a dedicated system for shape analysis, where you can get 13 parameters like circularity, depth, and everything you will get from that particular system.
Okay, sir. Okay, sir. Thank you.
Thank you, sir. Now, I would like to hand over the session to Ms. Aparajita Borwa, Membership Chairperson, SPE, Dibrugarh University Chapter, to continue the session.
Thank you, Pujari. Am I audible?
Yeah.
Okay, thank you. Respected faculty members, the speakers, our most valued invitees, ladies and gentlemen, it's my privilege to have been asked to propose a vote of thanks for the session. I, on behalf of the SP Dibrugarh University Student Chapter and the participants around the globe, and on my own behalf, extend a very hearty vote of thanks to the speakers for gracing our session with your vision and sharing with us your findings and opinions today on the topic Importance of Rheology and Particle Size Characterization for Petroleum. I would like to mention Mr. Rajkumar Somenjit Singh, Regional Sales Manager, Anton, Parr, Northeast Division, for helping us to reach out for the speakers. A big thank you to Dr. Kartik S. Pondicherry for his efforts towards explaining the importance of rheology of petroleum products and different test methodologies and temperature dependencies. So your daily life analogy were very helpful in visualizing the concepts. And I must mention our deep sense of appreciation and our sincere thanks to Mr. Sudhanshu Trivedi for giving an excellent coverage on the particle size and its characterization method and analyzers along with industrial hint of particle size. Overall, it was very insightful session. Thank you speakers for sparing us time from schedule. We look forward to more engagements with Anton Parr, and we wish you all the very best for your future endeavors. Finally, I would like to take this opportunity to place on record our hearty thanks to the faculty members of the Department of Petroleum Technology of Dibrugarh University and the faculty members of Dibrugarh University Institute of Engineering and Technology who have blessed us with your presence. And also we have been fortunate assisted by our faculty advisor, Dr. Borkham Das ma'am, who have been a constant support and guidance. And last but not the least, thank you everyone in the participants for making this session a great success with your presence. Before we conclude, I would like to make a small announcement. Our SP student chapter, in collaboration with Technogate, is organizing a national level quiz competition on 2nd of July 2020 at 5:30 p.m. IST. The questions will be mainly related to petroleum background, and also we are giving out various prizes worth 10,000 INR. We have posted the e-flyers with heading Petro Prodigy in our official handles. Those who don't know about the same may contact our team members or can directly contact us through mail for more information. The registration link will be active till 8 p.m. IST of August 2020. And those who have already registered, information regarding the commencement of the quiz will be sent to you through your registered mail ID only. So thank you everyone. Have a good day ahead.
Hello, how can I register?
Yeah, you can register. You can mail us on our email ID. We will provide you the information.
So on behalf
Yes,
of Anton
we will.
Parr, I would like to thank everyone, and Ms. Ajita, thanks for the vote of, thanks, and the organizers for this excellent congregation. So please stay safe and take care. Thank you.
Thank you.
Thank you.
Thank you, sir.